pace here as we come towards the end. I actually expect that we'll have some time for some working sessions as we close out the term here, for you to get to work on your projects and so on. I understand that's a lot of work, so I do want to give some class time in that regard. And it looks like we will not have a great deal of difficulty finding some, which I'm pleased about. And next time we'll look at secondary compression. I don't think we'll get to that topic today. It's a quick topic, by the way, but it is a separate one. I'd like to look at the spring and piston analogy. This was present in the video lecture that I'll presume you viewed or have seen in 381, in which a load is applied, in which you have a delta sigma being applied. And what happens there is the oil pressure in this piston is in this cylinder is holding that water pressure, excuse me. And it's only with time that this valve leaks that oil out, drip, 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 which allows for compression of the spring and a downward motion of that cylinder, and therefore, or of that piston, I should say, and therefore a compression of the soil skeleton, which would be the spring itself in the analogy that is being utilized here. And after a great deal of time, settlement has occurred. This is at a lower elevation. This returns to atmospheric pressure. The oil in here will return to atmospheric pressure. So there is no longer that delta sigma in place. If we look at this trend with time, we see that total stress goes through a jump. It's usually shown as a step of some sort. And this version of the graphic is actually accurate to a level of showing a construction period, which is depicted here by the slope of this curve. So that might be happening over some weeks, months, even years that would occur. And it's more or less a step load that all of the building was not there, and all of a sudden the building is there. And it took some time for that to be placed, but not a great deal of time in the large context of time on the geotechnical scale. And if this is an embankment, the delta sigma would be a gamma of the fill material, a gamma compacted, if you will, times a height of that fill. Same as the embankment type Q naught that we've been working with so far. And what this is getting at is if it's a huge embankment, large spread, covering a great area, there's actually no distribution of the stress. It just gets treated like a whole nother soil layer being placed on top. And in that effect, it just shows up as gamma times H, like a new soil layer. And if we look at the pore water pressure, that similarly extends upward at the exact same moment by the exact same amount as this delta sigma. In other words, what's happening here is water pressure is holding that load for this instant. And it is here that the water pressure, the excess water pressure, will dissipate to the surrounding area. For calculation purposes, we're going to make some assumptions in this regard and say that that's going on one-dimensionally, only vertically. That's a bit of a stretch, but it's fine and keeps the mathematics on this thing quite reasonable. Whereas if you get into 3D, it starts getting a little bit involved. And the effective stress would then be the difference between these two. And what this states is the moment, if let's say Superman comes along and places a building at this instant in time, the moment that occurs, there is no change in effective stress. The grain-to-grain contact stress in the soil matrix has no change. In other words, the soil doesn't even know that the load is there. It's being held entirely by that water. And it's with time, as that water pressure dissipates, that it is transferred over slowly to the soil skeleton or to that spring that we showed in the previous slide. So I'd like to explore this a little bit, not just from a time perspective, but from a space perspective as well, and kind of bring these two together. And to do that, I'd like to consider a fine-grained soil layer, such as a clay, and that's what we'll be considering in this class for consolidation, is fine-grained soils, or at least soils containing some fine-grained component in them. And at the moment, I have that clay layer surrounded by two sand layers, and that's just for example. And we'll look at some different examples later today as we go along. But I'd like to show what happens in that clay layer when loading is applied. So the moment loading is applied in this left diagram here, this left block, it's an initial increase in water pressure, and the delta U shown on the x-axis is the same as delta sigma, and it's consistent all the way throughout the depth. Delta sigma would be the same. And this is a somewhat simplified model of this, and it works real well if it is a huge embankment getting treated like a new soil layer, where it is indeed like this. There are more complicated versions where you can have differences in this regard, where the stress distribution actually changes with depth, and I don't intend to explore that much in the class, but I do want to allude that, you know, that sort of nuance is available for study and so on. I would rather have you really understand this aspect and take that as needed as an add-on in the future as you need it in your careers, kind of thing. And I think you'll take it right in stride if you get the strong foundations here with this stuff. Now, what is going on here? This is stating that an embankment is placed on top on the ground surface here. Let's say where the pin is. So that's an embankment load. And the embankment loads the water pressure immediately throughout the entire depth by the same amount. So you have this delta U, a change in water pressure, and that delta U is equal to delta sigma that we spoke of earlier, which is due to simply the embankment load. With time, this extra water pressure in here, excess water pressure it's called, is able to dissipate. It has a tendency to dissipate. It wants to dissipate. There's actually a gradient that is produced, and you have this high pressure in this zone, and you have a lower pressure in the sand layers. So indeed, this extra water pressure wants to drain towards the sand layers. And you could imagine that the particle of water right next to the sand at high pressure is going to dissipate. And which direction would that travel if it's going to dissipate? Anyone? If there's a water particle here, right next to the sand,
it would travel up?
It would travel up, correctly. Thank you, Evan. And how about one down here? It would travel down similarly. And how about it here?
It's more likely to go down.
More likely to go down. You're below the midpoint, so it would tend to go down. Thank you. And I think that was Kurt. And it would take on this shape where immediately, right after a time zero, actually it would still have almost full pressure right at the middle. Nothing has happened there. There hasn't been time for it to drain from the clay. Remember, clay is, 1 times 10 to the minus 7 centimeters per second or something for a K. So it takes a good deal of time for water to flow out of this in the first place. But at the edge, it's able to drain out. And shortly after that loading, it's going to have a look something like this, where it will stay with a good deal of excess water pressure, excess pore pressure at the middle of that clay layer, yet it will drain at both drainage edges. And that is doing so on both top and bottom because we have sand, on both top and bottom. That was highlighted at the beginning of the problem. We actually are allowing drainage in this example, both directions. So it will tend to look like this. And the distribution that results is parabolic. And what happens with time is you'll progress along different parabolas and it will shrink with time, something like this, and continue down to where it's just a little sliver. And it will take a very long time for this process to occur. This is something that occurs over weeks, months, years, even decades would be the consolidation process, the normal timeline for that kind of process. So with time, this is dissipating at the boundaries. So you're allowing for that extra water pressure to drain outward and become a parabola shape instead. And that's all starting with the initial increase of a rectangular shape prism of extra water pressure that is similar throughout the entire depth. And I'd like to explore this a little bit more and think of it a bit theoretically from a flow standpoint and relate this to Tertzagi's one-dimensional consolidation equation. You've heard his name a lot in the class from bearing capacity. Well, he also came up with consolidation theory in geotechnical engineering, as well as effective stress. So he certainly changed the course of geotechnical engineering with his thoughts and direction on theories. And if we look at one of these parabolas, just an example parabola at some time t, and we take a little slice of soil out of there, and we say that that slice of soil is dz or del z, depending on terminology that we're using, infinitesimally thin little soil element here, we can consider the flow through that element to be Q equals KIA. Hydraulic conductivity times hydraulic gradient times area. Well, area will go away. We'll make that, conveniently equal to 1 or something like that, or in the coordinate system provided here, dx dy or something like that. I would be the amount of change in total head over the distance traveled. So the distance traveled is going to be dz, and the pressure loss going through that will actually relate to the slope of this, the localized slope of this parabola. You could imagine that if this is right here, you're not going to have a large gradient pushing that one way or another. However, if it is right where it's shown, there's quite a bit, and it continues to increase as you go further. As well, separate from that altogether, you would have a compressibility. of this soil element. So if we look at how will that element compress, actually just, geomechanically, this is hydraulic framework of thought, and this is now geomechanical framework. And if we consider the geomechanical, the compressibility of the element is going to be related to this stiffness called A sub V. And A sub V is defined as the slope of a void ratio versus effective stress plot. And whether you recognize it or not, you've seen this plot often. You've seen this a lot, including if you watch the consolidation video. You certainly saw this, but you may not recognize it because usually this is shown as a log scale. And usually this shows up as a bilinear trend, where we have a C sub R or a C sub S as the shallow slope and a C sub C for that steep slope, and a pre-consolidation stress as the knee of the curve. So that's the normal mode of showing this. But if we just zoom in on a little part of that graphic and show it on an arithmetic scale of just regular old sigma prime, it actually shows up as a curve looking something like this, concave upward. And part of Tertsagi's formulation is that he's assuming we're only talking about small increments of stress, so small changes on this axis. And what can be calculated from this plot is a compression, a delta E, because you would have some known delta sigma, say between here and here. That would be your delta sigma. And we could use the slope to arrive at then a delta E. Use the run to get the rise, in other words. That's all we're doing in that case. And we know the slope is A sub V. And a real conceptual point here that Tertsagi was able to see through, I think both of these, while requiring critical thinking and so on, are quite straightforward. Another that really puts the puzzle together is that there's continuity. And the flow, Q equals KIA, must equal compressibility. These two quantities must actually volumetrically equal one another. The amount that is flowing out of this specimen in an upward direction, in this case, up here, and the amount that that same specimen is compressing on a volumetric basis, those two have to be the same. And I have not written down here the equation for the volumetric amount of compressibility. I've only shown the slope, and I'm describing in words the calculation itself. But if you bring these two together and equate them, it would look something like this. And to do this, we bring in something called a composite parameter. And that's called the coefficient of consolidation, C sub V. And it's a really nice parameter. It's a heavy-hitting parameter. It brings together both hydraulic aspects of soils and compressibility aspects of soils, and shows up in a diffusion-style equation like this that describes the entire process of consolidation. And this is the KIA aspect. This left side is the flow regime. So here's how much flow is going through that element. And over here are how much flow is being lost from that element. And on the right side is the compressibility of that element. And that would be AV over 1 plus E naught, del U, del T, and these are changes in water pressure. The U's are water pressure, T's are times, and Z is vertical distance, of course. And if we simplify or rearrange this and introduce this composite parameter C sub V, it cleans up pretty nicely to just be this one term on each side equation, CV times del squared U del Z squared, and that's equal to del U del T. And that is a common form of diffusion type equations, energy type equations. You'd find the heat equation looks to be this format. It is all really the same thing. You can look at voltage. It ends up with similar sorts of equations and so on. Any kind of energy source would be that. This just happens to be a hydraulic gradient we're speaking of. And this is known as Terzaghi's one-dimensional consolidation equation. So this is a biggie and allows us an opportunity to solve for the amount of pore water pressure dissipation at a given time at a given depth. And C sub V is defined at the end here. And that is K, hydraulic conductivity, over rho W, density of water, times G, acceleration due to gravity. So the denominator here, you could rewrite that even more cleanly as just gamma water, times 1 plus E naught, initial void ratio, over A sub V. And this whole expression here is known as the coefficient of consolidation. And that coefficient of consolidation brings in, as I mentioned, hydraulic aspects, K, and compressibility aspects, A sub V. So both how easily water flows through the medium and how squishy it is in very casual terms. And we will work with a closed form solution of this, which will make it quite manageable, by the way. And if we're going to quantify how much consolidation, how much of the consolidation process is complete, we can consider a discrete point somewhere among the depth of that clay layer, for instance, and we would need that version in order to evaluate a specific change in a specific excess water pressure at a given time. And that allows us to get to an effective stress at a specific location within the clay layer. And sometimes you need that for whatever reason. You need to know what is the effective stress at this location in 2023 or whatever, your problem is encountering. Another one, you can consider the entire layer, an entirely different approach to the problem, and even using different parameters. And that would be the entire layer. And this is needed to evaluate the settlement at time t. And this is probably a little more practical or a little more common of a need than this top one. This is nice, a little bit academic. It's not, all that common that you need to know effective stress at a given time. But hey, there are times when absolutely it's exactly what you need for a highly practical reason. So I'm not trying to discount this, but absolutely the entire layer version you use all the time. That is an extremely common calculation. So the two calculations that would be undertaken look something like this. We have the starting point shown here with a rectangle. And I'll presume that rings a bell from a previous graphic in this image series that that is the delta U at the onset due to a delta sigma being applied up at the surface, an embankment, for instance. And we have this parabola of remaining pore water pressure. Okay, and that would dissipate with time and dissipate with time and dissipate with time until it becomes just a line over here. And we have a parameter here called degree of consolidation. And that is known as the capital U. And I'll write that here, I'll define that. Degree of consolidation. Degree of consolidation, capital U. So that would be how much consolidation is complete at that distinct point. So for instance, this point here is highlighting at this exact time when this parabola is present, whenever that happens to be, sometime after loading. What is the degree of consolidation at that point? And we would say that it is 0% complete off to the right, as I've shown it, and it is 100% complete when it is all the way dissipated to the left. Just a fair warning, sometimes you see these graphics, even in a handout that I think it's part of today, these parabolas end up being flipped. And that is valid, they're still the same thing, so it's just a matter of preference on which way you have the sign convention going. I'm showing it as a delta U, so to me, this is a larger value. In the cases where it's a parabola going the other way, sometimes it's shown as a sigma prime value, an effective stress value, and you're approaching that higher value with time. In any event, this degree of consolidation is 0% over on the right and 100% over on the left. So when this gets to be just a little sliver of a parabola, it means you are entirely done with the consolidation process. And when it is literally a line over here, that's when you'd be done with consolidation. Theoretically, consolidation takes an infinite time to be completed. So, it's kind of like waiting for election results. It takes a while. In any event, there's another approach that speaks of the average for the entire layer, and that's called U average. And I'll show that one in red. And that would be the average degree of consolidation. Capital U sub average. And I'm estimating that to be about here. And what that means is you are, I think Holtz and Kovac's textbook has some nice integrals to show what this is and so on. You're taking this area under this curve, under the parabola, meaning to the left of it, divided by the height of it, divided by the distance here. And in effect, what you're doing is making an equivalent rectangle from the area of this parabola. So I hope that makes sense for you from that perspective. And you could consider this to be a block like that in area that represents the area under that parabola, to the left of that parabola. In other words, this little triangle down here plus this little triangle up here would add up to be equal to that little bubble out there to the right of that red line. So we are taking in sort a weighted average of that parabola shape and saying that's an equivalent rectangle for it. And the way that I've drawn it, I'm guessing it to be, I'm approximating it to be 52% based on this rough diagram here. When this is done properly with calculations, you'll be able to calculate numbers and so on for this. But I am hoping with this sketch and introduction kind of content that you understand what calculation is being made in the first place. So you can see that by all means, a portion of the layer is 100% consolidated. That would be right at the sand and also right at the sand for a double drain layer. And another portion is only 20% done because it's only a portion of the way in here. But overall, that entire layer, if you just average it out over that whole layer thickness, it's about 52%, meaning it's a little bit this way, a little bit left of halfway, just slightly. That's why I was picking 52. And all of this on this page relates to this shape here, which we kind of saw earlier in terms of the schematic with the clay layer surrounded by sand. And what this shape represents is that you have some water pressure, excess water pressure remaining in this shaded zone. And we have dissipated water pressure over here. So this portion on the right, call it the white shaded area, has already been transferred to the soil skeleton. This portion here has not, in the blue shaded region. And if you need to calculate direct quantities, the way that we'll do that is to work with what I like to call kindergarten fractions. And a U average is the amount that's been dissipated over the original amount. Alternatively, you could say it's 1 minus the amount remaining over the original amount. And either of these would get you to the right approach. We actually will not be having to work with areas and sketching out parabolas and estimating things and so on. It will be taken care of with a closed form solution. So you'll have some equations that take care of this for you. But again, I do want you aware of what you are calculating in the first place, so you have a sense for it and a sense of reality to be able to do, I'd call it a reality check as you go through problems. I would like to look at the closed form solution for a minute. And this is a depiction of those fractions I was just showing. So this has the reverse parabola shown, the kind of mirror image of what I was depicting, but it is all the same thing. And the closed form solution looks like this. We introduce a dimensionless time factor, capital T. And capital T is equal to this coefficient of consolidation, which we defined earlier, that composite parameter, times little t, which is real time, and that real time can be in seconds, minutes, months, years, whatever units you're working in. You just need to be careful that you have consistency in your units between time and CV, and also drainage distance down here and CV. So H sub dr is the maximum drainage distance. And that is going to be a function of whether you have a single or double drained system. We will work in this class with vertical, one-dimensional type drainage situations. And I'll allude to some others, and I can talk to them as we go along, talk about them, I should say. But I will not be getting into much in the way of calculations with those and having you be accountable for that. But I do want you to kind of see where this stuff goes at, I'd call it the next level of calculations and so on. And that T can be plotted out like this. And this is a series of those parabolas with time. So here you are approaching a complete consolidation, in this case over to the right, where complete consolidation would be where you have a line over here. 0% consolidation would be the initial point where you have a full rectangle here, and that's the 0 here. And with time, initially what happens is that soil right next to there, the water right next to the sand layer down here, is able to drain. So it goes from a 0% consolidation immediately down to 1 or 100% consolidation. And this consolidation ratio here is the same as what I had identified as a degree of consolidation. Same thing. And I do have some handouts here for you, so don't worry about trying to, get all this stuff firsthand. Just I hope that you can, see it and be able to recollect it if you look at this material again, which I expect may be the case for some assignments and so on. This is a normalized height where Z, capital Z, is little z over H. And H is a real common parameter used for height of layer in consolidation analysis. So that would be the entire height of, say, a clay layer. And if it is double drained, you would have a value of 2 here. And if it is single drained, you can actually chop off half of this diagram, and it's still a valid analysis mathematically and so on, and you would only work with half the diagram.
When you're saying a single or doubly drained, are you talking about draining upwards and downwards depending on what the adjacent layers are made out of?
Absolutely. That's a good description of it. Thank you, Kurt. for clarifying that point. If you have sand above, sand below, that would be called double drained, and it would look like these full parabolas. If you had sand above and impervious bedrock below for a given situation, you would have a situation that would look like the top half of this diagram, where it would simply be a maximum excess pore pressure right at that interface with the impervious bedrock, and would dissipate downward quite slowly at that far interface. And up at the sand, it would be dissipating readily and do so right away to bring in this half a parabola shape. Thank you for highlighting that.
What if you have asymmetric drainage conditions? Like what if you had gravel on the bottom and silt on the top or something like that?
You would bring in a more sophisticated numerical solution, such as a finite difference approach. And I will say that in this class, we will have clean drainage conditions. It will either be on or off sort of thing. But you would require either a finite element analysis or finite difference type analysis to get through a problem that you're describing, where you have silt versus sand or something like that. Good question. If we look at the average degree of consolidation, this U average, it is related to settlement at some time t. So the settlement at time t is S sub t, and I'm using a capital S for settlement here in this notation, in this set of graphics. I think Salgado is still utilizing W sub C or something for consolidation settlement. He likes that W for settlement. Just be aware of that does exist. But I'll be consistent here with a capital S. It's a very common terminology, by the way. Discipline-wide, you can go to 15 geotech textbooks and you'll find 14 of them have a capital S for settlement. So I don't feel out of step with this. It just happens to be out of step with Salgado. In any event, settlement at some time t, 6 months into a process or something like that, we went through that fiber optic problem, and there is something in that regard where you'll be estimating settlement some months into the process, is going to be this U average, how much settlement has occurred, or how much consolidation process has occurred, times the ultimate primary consolidation settlement. So the ultimate, just regular old capital S, is from the regular consolidation type calculation, where you would have this kind of graphic. An E log sigma, a void ratio, log sigma prime, bilinear curve with a pre-consolidation stress, behaving as a knee on that curve somewhere. And you would need to sort out whether you are up in this region, in other words, over-consolidated, whether you're down in this region, normally consolidated, meaning starting at the knee of the curve, or if you're starting over consolidated, starting to the left of the knee of the curve and ending to the right. So you're actually going through that knee of the curve utilizing both slopes. And the result of that calculation, which I'll presume you guys are pretty well up to speed with the theory and so on for that, and the calculation modes, that kind of thing. That's the ultimate. So that's the amount of settlement that's going to happen at time infinity. And this just allows you to say, all right, we're talking about a fraction of that. In the example I showed a few images ago, it would have been 52% of that would have been completed at that stage of the consolidation process, because U average was 52% with that depiction. And the equation, just rewritten a little bit differently, but not much. I've just added these subscripts here. A little box on both the big T and the little t. That box implies U average. And that this equation represents a snapshot in time. So you are, with this equation, describing one parabola. I'll go back to the parabolas here. You're describing one of these. Oh, I'm sorry. You're describing one of these parabolas. That's it. I'm tracing the one here with an A on it just by chance. And the mathematics associated with that time factor are describing that one parabola. So it is a snapshot in time. And what that means is that you have to be talking about the same parabola with both real time and this magical time factor, which is taking care of all kinds of crazy mathematics in the background. Sorry about that. And allowing for a valid solution for one point of interest in time. And this equation will be valid as long as that subscript on those two terms is in fact the same. And it can be T50. Large T50 is CV times little t50 over h stranded squared. It can be 90. Large T90 equals CV little t90 over h stranded squared. It can be 34.3. Large T 34.3 equals CV little t 34.3 over h stranded squared. Any of those is valid. You simply can't be mixing apples and oranges, because then they won't talk to each other. It is describing one given parabola, and you have to have both sides on that same page of calculation, that is actually what's being addressed. So there is a relationship between large T and U average. And there are two equations available for it. One is for large U average, these are less than 60%. And that would be large T is pi over 4 U average squared. And there's a different one for U average greater than 60%. And that would be a large T is 1.781 minus 0.933 times the log of the fraction 100 minus U average. And sometimes you don't know which case you're in. So what you can do is just jump into one of these equations. And if you come into the correct range, you know you've selected the right one. If you're off range, it means you selected the wrong. You can go to the other and hope that that remedies that situation. Questions at this stage related to overall manipulation of these equations and so on?
Is the settlement we're calculating the total settlement for the clay layer?
It is the total. Let me back up a slide here. This S would be the ultimate primary consolidation settlement. That's the total consolidation settlement. So that does not include immediate settlement. It does not include secondary compression, but it's all of the consolidation. It's the total amount of consolidation. And at some time T, some fraction of that will have occurred. Does that help, Eileen?
So in calculating the total settlement, we would add this settlement at time T to the immediate settlement and the other settlement factor.
It would be quite common to, yes, you'd want to add it to the immediate if being asked. I'll say, in this class, it will be quite specific what is being requested of you to solve for. But in a practical type problem, immediate will happen first, and immediately, as the name implies, and then primary consolidation. So any fraction thereof would get added to that as a total amount of settlement. And secondary compression is typically assumed to begin only after this primary consolidation is completed. So it's after quite a long while that process takes hold and can be documented to be calculatable. So the first two, chronologically, it would be immediate settlement, then consolidation, then secondary compression. And I would say you could follow them chronologically and take any of interest up to that point of the project or up to that stage of inquiry on how much settlement has occurred, if that makes sense.
Okay, thank you.
Absolutely. Other questions? Okay, looks like a good time for a break. Let's do that and say 10, 11 minutes, so 3:15 we can get back. How about that?